galaxies takes its sweet time to traverse the vastness of space before it graces our sight. Gazing at Betelgeuse, you're actually witnessing a spectacle from 650 years in the past. To put that in perspective, when this very light embarked on its journey toward Earth, the Renaissance was just dawning, and explorers like Marco Polo were making their mark in history. Every observation we make of Betelgeuse is like looking through a cosmic time capsule, granting us insights into its distant past. And if, for argument's sake, Betelgeuse had already exploded in a magnificent supernova, we would remain oblivious for another 650 years. So while we discuss and predict its impending supernova, somewhere out in the vast cosmos, this monumental event might have already unfolded. We're just waiting for it to traverse space and time until it reaches our eager telescopes. The recent revelations around Betelgeuse have led to fervent discussions in the astronomical community, with comparisons being drawn to another sensational discovery from earlier this year in 2023, SN 2023X. This recently observed supernova occurring in a galaxy neighboring the Milky Way reminded many of the fascinating dynamic and unpredictable nature of the universe. SN 2023X was unique in its own right, located several million light-years away, showcasing an intense display of brilliance that momentarily outshone its host galaxy. But what made it particularly interesting to scientists and casual observers alike was its uncanny resemblance to what many predict will be the fate of Betelgeuse. The spectrum, intensity, and aftermath of the explosion offered a tantalizing glimpse into the processes that these massive stars undergo as they approach the end of their life cycle. For many, SN 2023X served as a preview of what Betelgeuse's explosive fate might look like. The sequence of events may look similar to what was witnessed with SN 2023X. In addition, the connection between these two celestial events underscores a broader theme about the interconnectedness of our universe. Whether it's a neighbor like Betelgeuse or a distant supernova such as SN 2023X, these cosmic phenomena remind us of the dynamic and evolving nature of space. The realm of space exploration is full of uncharted territories and unsolved mysteries, and nowhere is this more evident than in our understanding of red supergiants like Betelgeuse. As brilliant as they are enigmatic, these celestial giants hide some of the universe's most profound secrets. At a fundamental level, the life cycle of red supergiants, though charted, is punctuated with ambiguities. While we know that these stars evolve from the main sequence phase to their grand supergiant stature, the intermediary processes are less understood. These phases, which might involve tumultuous upheavals in the star's core, are still subjects of intense research and debate. Second, red super. Giants are known for shedding massive amounts of material in their later stages. This process is crucial in shaping their evolution and eventual supernova explosions, yet how they lose this mass, at what rate, and what triggers these outbursts remain unclear. Betelgeuse, with its recent fluctuations, only adds to this prevailing uncertainty. So, what are the implications of a Betelgeuse supernova at the heart of this cosmic drama? An event of stellar proportions is set to occur. Dr. Stan Meff from Western University suggests that when Betelgeuse does finally explode, it will momentarily be one of the brightest objects in our sky, outshining all other stars and possibly even some planets. For context, even at its vast distance of 650 light-years, the luminosity could rival or even surpass that of the Moon. Night would turn into a pseudo-day for weeks or possibly months. This blinding display would last for weeks, forever changing our perception of the constellation Orion. The following months would see this luminosity fade, and after decades, an outer shell of the once vibrant star would present itself as a planetary nebula surrounding the dim remnants of its core. Astronomers and astrophysicists worldwide are evaluating the potential effects of such a spectacle on Earth. There's some speculation that an explosion could release cosmic rays, high-energy particles that travel through space at nearly the speed of light. These particles would race across space, potentially colliding with interstellar material and ionizing it, leaving a trail of charged particles. When these cosmic rays approach Earth, they could interact with our magnetosphere, producing some gorgeous auroras. But does this mean we're likely to face serious consequences here on Earth? Thankfully, Betelgeuse is far enough away that these rays would likely be diluted and absorbed by our atmosphere, ensuring minimal impact on our planet's biosphere. While the explosion itself won't pose a direct threat to Earth, the cosmic light show will undoubtedly spark conversations, research, and possibly even concerns. Beyond the tangible and scientific, the explosion would have profound effects on human culture. The sky, observed and revered for millennia, would have changed. This alteration would lead to reflections on impermanence, the vast scales of time, and our place in the universe. Such cosmic wonders remind us of the ephemerality of existence and our eternal quest to comprehend the great beyond.
If you go to the early universe right after the Big Bang, it was expanding way faster than the speed of light. Just like how CERN presented the heliocentric model, we may be in for another mind-blowing revision to our cosmic understanding. A debate has arisen in cosmology known as the crisis of cosmology. Neil deGrasse Tyson has said that the James Webb findings have ended this debate in a physics-shattering image. So, what exactly is this crisis, and how has the James Webb Space Telescope contributed to it? For some, it's hard to call it a crisis. It is a crisis, but for some old-timers, it's really hard. There was a time when we didn't know the age or size of the universe because they are related within a factor of 2. Join us as we venture into the very frontier of science, where our knowledge is constantly put into question and where we're making unanticipated discoveries. Over the past century, a significant achievement in cosmology has been the establishment of a standard model outlining the universe's history and its current state. Gravity, guided by general relativity, primarily dictates the universe's evolution, explaining both its expansion and the formation of large cosmic structures. The known components include dark energy, dark matter, normal matter, neutrinos, and photons. The universe originated from the hot Big Bang around 13.8 billion years ago, preceded by cosmic inflation, which caused density imperfections. But what if we told you that this very model is now under scrutiny? This model has been responsible for our understanding of the universe for the past century or so. Despite extensive observational support, this model might be incomplete. While we're getting more and more observations, each new one has to be examined in the context of the model to see if it still holds up. But astronomers have gotten a new tool in their toolset with the JWST, and this device has been creating problems for our standard model. It all started in the early universe before stars or galaxies emerged, when neutral atoms were forming around 380,000 years post-Big Bang. Then, 550 million years later, reionization occurred, ionizing most of the universe. The initial waves of reionization started approximately 200 million years after the Big Bang, with some stars possibly forming 50 to 100 million years after. The JWST, with its capabilities, allows astronomers to unveil more distant galaxies than previously possible, offering new insights into the early universe. First, let's go through what we know. The standard model of cosmology, known as the inflationary hot Big Bang or lambda CDM, has been remarkably successful. It explains various features of the universe, including gravitational lensing, the cosmic web structure and growth, the internal motions of galaxies, their relative movements within groups and clusters, and features in the cosmic microwave background. This model predicts that as we look further back in time and cosmic distances increase, the observed galaxies should be inherently smaller, bluer, less developed, and less rich in heavy elements. At some point beyond our current observational reach, we anticipate entering the universe's dark ages, devoid of visible stars or galaxies. But while verifying the integrity of these explanations, scientists have found conflicting evidence, resulting in a crisis of cosmology. The cosmology crisis is simple: we don't really know the age of the universe. Different methods give different results, and it's up to cosmologists to find out why, but they're struggling to do so. Let's take a look at the methods we use to measure the universe's age. The first one is cosmic background radiation. To unravel this cosmic mystery, scientists delve into the universe's expansion history, and to do that, they need mathematical modeling. This modeling is based on Einstein's general relativity theory. Applying this theory to the entire universe produces the Friedmann equations, linking the universe's composition, dark matter, dark energy, radiation, and more with its expansion rate at specific times. By measuring these contents, we can get the age of the universe using the cosmic microwave background CMB to do just that. The CMB is the remaining light from the early days of the universe when it was about 380,000 years old. It is a crucial tool in measuring the universe's contents. Exceptionally detailed maps of the CMB provide insights into the universe's composition. One such map is from the European Space Agency's Planck mission. But there's an issue with these maps: they lack data on dark energy, which is a significant player in the current universe. Dark energy didn't influence the early universe, so scientists must incorporate its effects manually based on other observations. Despite this, scientists can use the Friedmann equations to figure out the expansion rate of the universe at any point in time. They can even figure out the expansion rate today, and through that, determine the age of the universe. Another way to measure the age of the universe is by looking at exploding stars. While the CMB provides a thorough record of the universe's makeup, it's a historical snapshot originating billions of years ago. Another way to measure the universe's expansion is by directly observing its rate of growth. Thanks to Type Ia supernovae, a celestial spectacle where a star dumps its atmosphere onto a nearby white dwarf, the remnants of a deceased star. When the white dwarf hits a critical mass, it erupts into a supernova. Since this cosmic drama unfolds similarly across the universe, scientists consider supernovae consistent benchmarks or standard candles. This means we know their expected brightness, and by comparing it to their observed brightness, we can estimate the universe's expansion rate at the time of the supernova. This method, employed in the late 1990s, played a pivotal role in discovering dark energy, becoming a cornerstone in cosmological measurements. The JWST has complicated things further. According to Neil deGrasse Tyson, the JWST has found things that, to our current understanding of the universe, shouldn't exist. Something had to change. Our current scientific understanding needs to be reworked, but we simply have no idea where to start. For instance, the JWST's recent images reveal galaxies much more distant and consequently older than anticipated by the standard cosmological model. This is yet another piece of evidence suggesting that our model needs updating. Hubble's groundbreaking revelation of the expanding universe relied on galaxies, and the JWST's images showcasing galaxies forming much earlier than current cosmological models predict have sparked a crisis in the field. So, how do we explain such a discrepancy? One solution proposes flaws in our CMB measurements, yet the Planck CMB measurements, among the most precise in science, have undergone extensive testing since their 2013 release, validating their accuracy. An alternative perspective suggests a potential gap in our understanding of dark energy. Perhaps dark energy varies over time, intertwines with dark matter, or involves another unknown factor. This possibility captivates theorists, sparking numerous exploratory papers. Lastly, the accuracy of supernova measurements could be questioned. Although more directly gauging the present expansion rate, supernova observations are not foolproof due to the complexity of exploding stars. If we don't completely comprehend the intricate physics, supernovae can't serve as a precise cosmological tool. A touch of uncertainty in supernova modeling could resolve the entire discrepancy. In conclusion, the crisis of cosmology remains, leaving scientists puzzled. However, the JWST's discoveries may be the key to unlocking the mysteries of the universe's age, composition, and ultimate fate. An emerging black hole emits ultraviolet radiation into the universe, stripping electrons from hydrogen atoms and enhancing transparency to UV radiation. After successive stellar generations, heavy elements and UV radiation become sufficient, allowing for galaxies to form. Gas quantities and stars collapse into gravitationally bound entities, uniting to form the first galaxies. While observational evidence supports key aspects of this narrative, challenges arise when integrating it into the cosmological framework of the expanding universe. The standard cosmological model establishes a link between observed distances expressed through redshift and the age relative to the Big Bang expressed in years. Distances are directly observed and are unchangeable values, while age emerges from theoretical constructs melding models of an expanding universe, guided by Einstein's general relativity and our comprehension of matter from the standard model of particle physics. Together, they explain how distance or redshift correlates with age, the duration since the Big Bang. The issue arose when the James Webb Space Telescope started operating. As soon as it started looking at distant galaxies, it found things that betrayed our current knowledge. It found galaxies much more distant and older than predicted by the standard model. The Hubble telescope had already hinted at this, but the JWST confirmed it. While the universe originated from the Big Bang, indicating its beginning, discrepancies emerge in the apparent age of the first galaxies compared to the age-redshift relations predictions. These galaxies seem to appear too early, which is impossible according to our current understanding. The foundational Big Bang model, depicting an evolving universe rather than a static, unchanging one, remains unchallenged, but there might be a need to update our understanding. Increasing evidence in the form of data keeps making us question this story. But how much needs to be changed, and what are scientists doing to get to the bottom of this? Turning towards even better equipment to answer these complex puzzles. One such venture is a project known as Flamingo. The Flamingo Project, part of the Virgo Consortium, engages in extensive computer simulations spanning from the Big Bang to the present to explore the universe's evolution. This program investigates the elements of the cosmos. Funding for this project was secured from the European Research Council, the UK's Science and Technology Facilities Council, the Netherlands Organization for Scientific Research, and the Swiss National Science Foundation. Throughout the simulations, detailed virtual galaxies and galaxy clusters emerge. Telescopes like the Euclid Space Telescope and NASA's James Webb Space Telescope gather data on celestial entities. The simulations will be compared to the observed data, letting us know how accurate the standard cosmological model is and if it really explains the universe's evolution to a good extent. Professor Carlos Frank, a collaborator in the Flamingo research and Ogden Professor of Fundamental Physics at Durham University, notes a pivotal moment in cosmology. He says that cosmology is at a crossroads. New telescopes are very accurate, and the information we get from them doesn't align perfectly with our theoretical models, which in turn raises questions about the validity of these models or potential biases. The precise simulations aim to discern whether these discrepancies challenge the existing cosmological framework. Previous simulations primarily focused on cold dark matter. However, astronomers now emphasize the inclusion of ordinary matter, constituting only 16% of the universe, and neutrinos when comprehending the universe's evolution. Neutrinos are minuscule, infrequently interacting particles. Led by Professor Jup Shea from Leiden University, researchers conducted extensive simulations to investigate the universe's evolution. President Biden has introduced the first image to be shown publicly from the James Webb Telescope. The vast depths beneath our oceans conceal mysteries beyond our wildest imagination's enigmatic remnants of history. Lost cities and eerie signs of things once alive lurk below the surface, waiting to be uncovered. But amid the allure of discovery, there's a tinge of unease. What if these submerged secrets weren't meant to be found? Dive in with us as we delve deep to unveil 15 underwater discoveries that have left even the bravest explorers trembling. Prepare to be both enthralled and terrified. The Christmas launch of the James Webb Space Telescope in 2021 was truly a remarkable event. It soared into the sky riding atop a powerful European Ariane 5 rocket. The launch site was amidst the lush forests of South America, adding a touch of nature's grandeur to this colossal event. Thousands of scientists from around the globe had poured their collective expertise and effort into this project for 3 decades, culminating in this momentous achievement. However, such grand endeavors come with enormous risks, and the possibility of failure loomed like a shadow throughout. Miraculously, everything unfolded with near-perfect precision. The telescope embarked on a journey spanning nearly 1,000,000 miles, enduring 30 days of travel through the void of space. Its ultimate destination was the enigmatic Lagrange Point 2, a place in space where gravity maintains a delicate equilibrium, and it remains opposite the Sun in relation to Earth's orbit. This spot had already become home to other space telescopes like the Herschel Space Telescope and the Planck Space Observatory. It was an ideal vantage point for the James Webb Telescope to begin its cosmic voyage. As the James Webb Space Telescope embarked on its cosmic journey, NASA unveiled its ambitious agenda, outlining 4 primary realms of exploration. First and foremost, the telescope aimed to witness the universe's inaugural burst of light, a crucial juncture in the cosmic genesis. It sought to probe the ancient celestial past, laying bare the enigmatic assembly of galaxies during the universe's early stages. But beyond this cosmic archaeology, the JWST was likewise poised to unveil celestial spectacles of the utmost significance. It yearned to peer into the cradles of stellar birth, shedding light on the genesis of stars and the formation of protoplanetary systems. Moreover, its quest extended to the panorama of planets, delving into the grand narrative of planetary existence, including the elusive origins of life itself. These scientific frontiers had long eluded comprehensive exploration due to the inherent challenges of scrutinizing the universe. Before embarking on its celestial observations, the JWST underwent a meticulous series of scientific tests and calibration procedures. Among these was an all-important examination involving the deployment of a remarkable protective shield designed to safeguard the telescope's delicate instruments from the relentless onslaught of the sun's heat and blinding radiance. Given the telescope's perpetual voyage through the cosmic void, this safeguard was nothing short of imperative. The sun shield, one gigantic construct composed of 5 strictly layered membranes, had been carefully folded, similar to a complex accordion. The unfolding process demanded a precise choreography of steps, each calibrated to ensure proper tension and alignment of every layer. The stakes were massive, as any misalignment or harm to this cosmic guardian could damage the telescope's capacity to observe the distant, enigmatic realms of the universe. With relief, it sailed through the initial test, setting its course for the next challenge. The upcoming task was to open up the telescope, another highly delicate procedure. Even though it was already precisely positioned, it needed to prepare itself meticulously to fulfill its cosmic duties. At the heart of the JWST lay its primary mirror, an intricate mosaic of 18 hexagonal pieces that demanded perfect synchronization to craft sharp celestial portraits. The prepping of the JWST was a ballet of complexity and fragility, entailing not just the unfolding of its colossal sun shield, but also the graceful extension of its support structure and the gradual unveiling of its primary mirror. However, the mirror's revelation marked merely the start of the artistry. Every element had to align flawlessly to enable the JWST to fulfill its scientific quest. Another intricate calibration test involved awakening Webb's scientific instruments one by one, as if rousing dormant senses. These instruments included the near-infrared camera, the near-infrared spectrograph, and the mid-infrared instrument, each of them possessing unique talents for gazing upon the universe, adding layers of intrigue to the mission. Equally, the telescope had to define its cosmic bearings, a process known as commissioning. This involved engaging the telescope in studying calibration markers and refining its aim, ensuring that its instruments were locked onto the celestial targets with pinpoint precision. All these trials were the guardians at the gate, guaranteeing that Webb was primed and prepared to embark on its odyssey and uncover yet unknown secrets of our universe. As these intricate procedures unfolded, a sense of anticipation swept through the scientific community. Everyone held their breath, hoping for success and knowing fully well that in the world of science, things often don't go as planned. To everyone's astonishment, the JWST sailed through every test flawlessly, an achievement that's nothing short of astounding. This monumental project brought together more than 300 universities, organizations, and companies from 29 US states and 14 different countries. Then, in July 2022, after enduring and conquering every challenge NASA threw its way, the James Webb Space Telescope received the green light to embark on its remarkable scientific voyage. NASA proudly announced that all 17 of the observatory's scientific instrument modes had undergone rigorous scrutiny and were now deemed ready for action. Like any other telescope, the JWST's primary purpose is to collect and focus light, revealing distant celestial wonders. However, what makes the JWST exceptional is the specific slice of the electromagnetic spectrum it observes. While our human eyes are limited to perceiving visible light, the JWST sees beyond, into a hidden realm of cosmic phenomena. It's a profound shift in perspective, opening new horizons in our quest for understanding the universe. The James Webb Space Telescope is like a cosmic heat seeker, similar to a futuristic night vision camera that's capable of gazing into the universe's depths, but on a grand scale. Its enormous size allows it to gather more light than any other telescope, letting it peer at even tinier, more distant celestial wonders. But here's the best part: it's stationed up in space, free from those pesky atmospheric roadblocks that often blur our view. That's why they call it the universe's watchful eye. But how does this marvel actually work its cosmic magic? Well, at its core, it boasts a colossal 21-foot mirror. This giant mirror grabs and bounces light back to the telescope's intricate instruments. And speaking of instruments, the JWST packs a quartet of them, each with its unique cosmic talent. First up, we've got the near-infrared camera, the JWST's main eye. This high-tech lens captures breathtaking images of far-off galaxies, nebulae, and other celestial marvels. Next in line is the near-infrared spectrograph. It's like a cosmic prism, breaking down light into its rainbow hues, revealing secrets about the objects it observes. Then there's the mid-infrared instrument, specially tailored to scoop up infrared light. It delves into the mysteries of the early universe, explores exoplanets, and even takes a closer look at our own solar system. Finally, there's the fine guidance sensor, near-infrared imager, and slitless spectrograph. These high-precision tools ensure the JWST points in the right direction and is extra sensitive to near-infrared light. With this combo, it leaves no cosmic stone unturned. Now, the real magic lies in understanding the expanding universe. As the universe stretches and grows, light from distant corners of space gets redshifted. This means the light's wavelengths get stretched out, making it appear redder than its original form. By observing the universe in this redshifted light, we can literally peer back in time, seeing the universe as it was in its early days. Imagine witnessing the birth of stars and galaxies and learning about the ancient conditions of our universe. The James Webb Space Telescope possesses a remarkable ability to gaze deep into the universe, a feat that essentially lets it peer back in time. The farther an object is from us, the longer its light takes to reach our telescopes. Consequently, when JWST focuses its lenses on a distant galaxy, it isn't merely capturing a snapshot of the present. Instead, it's like a cosmic time machine, revealing what that galaxy looked like billions of years ago when its light embarked on its interstellar voyage. This unique capability allows scientists to delve into the ancient history of our universe, a time when the first stars and galaxies were taking shape, providing an invaluable opportunity to study the processes that sculpted the universe we now behold. The capabilities of the JWST made their grand entrance into the public eye on July 12, 2022, following NASA's unveiling of its inaugural batch of scientific imagery during a live event. These pictures were nothing short of breathtaking. Imagine staring at the cosmic cliffs within the Carina Nebula or gazing upon the ethereal beauty of the Southern Ring Nebula. These were more than just pretty pictures, they were windows into the vastness of space and time. But that's not all. The telescope equally went beyond aesthetics, diving into the scientific nitty-gritty. It analyzed the composition of the atmosphere of the scorching gas giant exoplanet WASP 96b, offering critical insights into alien worlds. Additionally, it presented us with a captivating quintet, a group of galaxies locked in a mesmerizing celestial dance as they merge and mingle. These images didn't just elicit excitement because of their visual splendor, though that was undeniable. They sparked enthusiasm because of the profound scientific revelations they brought. But it was as far back as February 2022 that NASA first offered the world a glimpse into the JWST's shocking capabilities. This was when NASA announced Webb's inaugural glimpse of starlight. The image, a mosaic composed of 18 scattered luminous dots, featured the prominent star HD 84406. Thomas Zurbuchen, NASA's Associate Administrator for the Science Mission Directorate, excitedly tweeted that as Webb honed its focus, these 18 celestial beacons would seamlessly merge into a solitary radiant star. This achievement marked a thrilling milestone, illustrating the telescope's immense potential for future discoveries and interstellar explorations. In the following weeks, Webb continued its odyssey of progress. On February 18th, NASA unveiled an upgraded image of HD 84406, where the 18 dispersed star copies had been carefully arranged into a mesmerizing hexagonal formation. This gave us a tantalizing glimpse of the eventual grandeur that awaited once the observatory precisely aligned the individual segments of its primary mirror, ushering in the era of image stacking that promised to unlock even more cosmic wonders. Webb didn't shy away from taking a daring selfie using The James Webb Space Telescope has made an extraordinary discovery, providing evidence of human activity far beyond the confines of Earth. This breakthrough brings us closer to answering one of humanity's oldest and most profound questions: are we alone in the universe? For centuries, humans have been fascinated with the possibility of extraterrestrial life, a curiosity that has sparked countless philosophical discussions, scientific theories, and imaginative works of literature. From the earliest days of civilization, we have looked up at the night sky, wondering about our place in the cosmos and whether other intelligent beings might be out there, sharing this vast universe with us. This fascination seems to be deeply ingrained in human nature, driving us to seek companionship, even if it is of an extraterrestrial origin. The recent discoveries made by the James Webb Space Telescope suggest that we are getting closer than ever before to finding the answers we seek. In 2021, the EB Space Telescope posed an intriguing hypothetical question: could our advanced technology detect artificial light on a distant planet, such as Proxima b. This exoplanet, located approximately 4.25 light-years away in the habitable zone of our nearest stellar neighbor, Proxima Centauri, has long been a subject of fascination for scientists. Proxima b was believed to be locked in synchronous rotation, much like the Moon with Earth, with one side of the planet always facing its star. This led researchers to hypothesize that if there were an advanced technological civilization on Proxima b, they might transfer heat and electricity from the day side to the night side using advanced solar cells. These cells would capture sunlight on the day side and generate electricity, potentially detectable by telescopes. A paper co-authored by scientist Manas V. Lingam proposed that significant coverage of the planet's day side with solar panels could indeed be detected by future telescopes. This raised the exciting possibility that the James Webb Space Telescope, with its more advanced technology, could one day make such a detection. Fast forward to 2024, and the James Webb Space Telescope has proven to be a technological marvel, with the capability to search for artificial lights or habitable exoplanets like Proxima b. Its enhanced sensitivity and extended range of capability mean that it can now detect phenomena that were previously beyond our reach. The possibility of finding artificial lights or signs of technological civilizations on distant planets is not just a dream anymore. The JWST may have uncovered the very light we've been searching for, a discovery that could propel humanity toward another monumental leap in its evolutionary journey. However, before diving into the profound implications of such a discovery, it is essential to understand how this scientific feat was accomplished. The mission of the James Webb Space Telescope centers around exploring the mysteries of the universe, with a particular focus on Proxima Centauri b. Throughout human history, we have been driven by the desire to answer fundamental questions about our existence, our purpose, and our place in the cosmos. These questions, though simple in their phrasing, are incredibly complex and have fueled human curiosity for millennia. In today's era of rapid technological advancement, we are closer than ever to finding answers to these age-old questions. While philosophers might argue that we are still in the early stages of understanding the universe, astronomers are excited to share the latest discoveries made possible by cutting-edge tools like the JWST. These technological advancements often go unnoticed by the general public, but they represent significant milestones in human evolution. The ability to observe distant planets and detect potential signs of life is no small feat. Now, with the world literally at our fingertips, we are poised to explore the universe in ways that were once unimaginable. The James Webb Space Telescope, as the latest heir to the legacy of human space exploration, is destined to answer some of the most fundamental questions about our place in the universe. It has already begun to shed light on the possibility of life beyond our solar system, as evidenced by its recent discovery of potential artificial lights on a planet light years away. Proxima b, also known as Proxima Centauri b, is a super-Earth exoplanet that orbits an M-type star. These types of planets, larger than Earth but smaller than gas giants like Neptune or Uranus, are a unique class of exoplanets in the universe. While much remains to be discovered about Proxima b, this recent breakthrough marks a significant step forward in our quest to better understand the universe and our place within it. The search for exoplanets has a long history, with the first possible evidence of an exoplanet dating back to 1917. However, it wasn't until 1992 that scientists were able to confirm the first detection of an exoplanet, a discovery that astonished the scientific community and opened up new avenues for exploration. Since then, thousands of exoplanets have been confirmed, with another notable detection occurring in 2003. As of April 1, 2024, a total of 5,653 exoplanets have been confirmed across 4,161 planetary systems, with 196 of these systems containing more than one planet. The majority of these discoveries are associated with M-type stars, also known as red dwarfs. These stars, while much smaller and cooler than our Sun, are far more common in the Milky Way galaxy. Despite their prevalence, observing red dwarfs can be challenging due to their low luminosity. Red dwarfs, with M dwarfs being a specific the star Proxima b orbits. The star itself emits very little light, with only 0.16% of the Sun's